Hello everyone, and I'd like to thank Terry for providing us a computer. We couldn't bring one due to the latest regulations. We couldn't bring one into the airplane. So I'm Cem, and my friends are Onurcan, Baturay, Bilge, and Mert. Today I'll be presenting our project about the informs. And you can just stop me if there will be any unclear points throughout the presentation. We divided our presentation into 5 main parts. In the first part, I'll talk about how we frame the problem, and then I'll mention some of our initial approaches to the problem, where we gained some insight into the data. And then I'll be talking about our game changer, the grading algorithm implemented, and some extensions to it. And in the fourth part will be regression analysis, when we forecasted the backsold of the soybean varieties. And lastly, I'll share our results with you. And now I'd like to start with the problem frame part. Once we decided that we'll be participating in this competition, the first thing we did was we started to do extensive literature research about soybean and its growth process. And during that process, we learned that some external factors like pH values, groundwater levels, and climate and soil was really important for the soybean growth. However, the data release lacked any kind of information that can be linked to those information. So at that point, we had to reconsider our solution approach from scratch. And actually, during that time, the webinar with Syngenta, which was actually hosted by Mr. Martin, was really helpful for us because we gained some really important information during that time. After the webinar, we got total clearance about the quality aspect and the importance of yield, and we learned some very important aspects of the relative maturity and how it was linked to the growth time of the soybean varieties. And also soon after we realized that the test data soybean varieties had only relative maturity values between 1.5 and 3.9, and this was actually a crucial point for our solutions in the future process. And speaking of solutions, I'd like to continue with our initial approaches, the relative performances approach and mean of use approach, where we gained some insight in data. In the relative performance approach, what we did was every variety for all of their replications, it was assigned a number of what percentage of other varieties and replications they outperformed in that location for that experiment. The problem with this approach was that there were great fluctuations between the replications, and we didn't know which replication actually gave us the real performance of the varieties. So just to overcome this problem, we thought even simpler. And in the mean of use approach, we basically take average of everything. First the replications, then the locations, then the experiments. But you would also would see after we implemented it, we saw that a fundamental problem with this insight, because it treated as if every location and every experiment had the same conditions, which was awfully wrong. At this point, we were convinced that we needed a more complex algorithm just to cover these external factors that we had no information about. That's where we started with grading algorithm. Now, in this section, I'll be talking about what it is and the extensions we made to it, which were the robust approach, the multi-instance learning approach, and weighted average yield approach. Now, what grading algorithm does is that it offers a failure grading. It was offered for a failure grading in the layer-based grading systems in universities. It adjusts the students' GPAs according to the toughness of the courses they took. So a student who took harder courses gets an adjusted GPA higher compared to the other students. Now, in the mathematical model, we have three types of decision variables, which are mu I, the adjusted GPA of student I, and mu j, which is the inflatedness of course j, and error margin, epsilon ij, which is the error margin of student I in course j. And we have only one type of parameter, which is psi ij, which is the grade of the student in course ij. Now, in the mathematical model, if you look at the first constraint, we explain the student's the grade of the student I in course j as the sum of the student's GPA plus the inflatedness of course j plus the error margin. And in the second constraint, we make sure that the inflatedness values of some of the courses are balanced. And in the objective function, we minimize just sum of the square of errors. Now, here we have a small sample of grading algorithm implemented to students. As you can see, Phil and Stu has the same exact GPA and same exact letter grades from different courses. However, when the grading algorithm is implemented, Phil's GPA is adjusted to 3.16, whereas choose is downgraded to 2.84. Now this is just the exact thing we want to do with our soybean varieties. We wanted to shift the varieties which were tested in harsh locations, the yield scores up, whereas we want to just little bit penalize the varieties which have been tested in like easier locations. And for us, this on the left, on your left, is a hard course for our case. And here you see an easy course for our case. Now, how we implemented the grading algorithm for soybean was we changed the adjusted GPA of student to the global yield value for soybean varieties. And we acted course inflatedness like the experiment location pairs inflatedness, and the letter grades in the courses became the yield performances of varieties in each experiment location pairs. Now, the problem addressed was the lack of information about external factors. We didn't know, as I mentioned before, anything about external factors. However, using this grading algorithm, the data told us. And the main takeaway of our grading algorithm was a global yield representative value for each variety, which will be used in the regression analysis for backsold forecast. However, as I mentioned before, we had a major issue implementing this into our problem, which was replications. We didn't know which replication to choose as the student's case. You can imagine this as a case where students have multiple grades for the same courses in universities. You cannot know which replication or which grade actually represents the student's actual performance. Now, to address this issue, our first approach was a robust approach where we accepted the minimum yield performance of the variety in an experiment location pair as that performance indicator. The main idea was, by testing varieties at their worst, we should find out the varieties which can perform well under all circumstances. Now, the advantage of this robust approach was, despite the nonlinearity of the objective function, it was convex and all of the objectives were linear, and we were able to solve the problem in Groby through its Python API in just like a minute. And however, we weren't satisfied with the results mainly due to two reasons. One, the objective value was higher than what we expected, and also, secondly, actually, the main issue was that Syngenta told us that relative maturity and yield was correlated in the problem statement. However, the results said otherwise, so we moved on to our second approach, the multi-instance learning approach. Once the robust approach failed, we didn't want to just force some replication to the model. Instead, we wanted to choose a replication just to minimize its error. So we introduced a new binary variable, gamma ijk, just to do that. And in the first and second constraints, when a gamma ijk is 0, they become redundant. However, we make sure that one of the replications for soybean varieties in each location and experiment pair is equal to 1 at the third constraint. And the other aspects stay the same. When we did this, we introduced 100,000 binary variables into the problem, and the problem became a very complex mixed integer programming problem. The optimality gap was 99.96% after an 8-hour run in a regular computer, so we concluded that it wasn't solvable in practical time. So we needed an approach, an easier approach where we didn't convert our problem into a very complex problem. And that was our last approach, the weighted average yield approach. And here, in this extension, we just questioned the need just to pick a replication out of in these locations. Instead, we wanted to assign the model, we wanted to let the model to assign different ways to different replications. And to do that, we converted our binary gamma ijk variable into a continuous variable, and we multiplied it with the replication's values. And in the third constraint, in the second constraint, as you can see, we made sure that the weights, the summation of the weights to be 1 for, again, for each location experiment pairs. So when we did that, we again made our constraints linear, and we were able to solve the problem just in like under 2 minutes. And the error was actually much more promising, well, 25% less than the robust approach, our first approach error value. And also, as I told you before, we got, and as you can see, actually, let me show you. And here we got the correlation between relative maturity and adjusted yields. Now, the graph, the first graph here you see is that it's just the intuitive methods results, and this is the grading algorithm's results. the points you see actually are the graded, previously graduated varieties, and the colors resemble the backsolve values. So the darker the color is, the higher the backsolve values are. So on the x-axis for the bulk graph, we have the relative maturity values. On the y-axis in this graph, we have the average yield, just where we took average of everything. And this is the adjusted yields, what we obtained from the grading algorithm. Now it is visually easily, you can visually see that after the adjustment, relative maturity values and adjusted yields become much more correlated, which was really promising for us. And this was obtained by the grading algorithm by shifting the, these points up and down the y-axis. And also, another promising thing we see that some of the dark points here have been shifted up after the grading algorithm, which is also very desirable for us because we want to see some high yield values being high backsolve values in the past, which we can be forecast in the future also. Now, speaking of forecasting, now I would like to continue with our regression analysis. When we were satisfied with these answers, we moved on to the regression analysis, where we tried two different methods, which is Mars and support vector regression. And in our regression analysis, as you can imagine, our main goal was to predict the backsolve values of class of 2014 varieties by using two independent variables, which are the adjusted yield values that we obtained from the grading algorithm and the relative maturity values, which was given to us in the data. And the dependent variable was, as I said, was the backsolve values. In Mars, as Mars allows some diffractions into the linear diffractions into the model, we thought it could handle the nonlinear relationship between the dependent and independent variables. However, as you can see from the heat map also, especially for the high and low relative maturity values, it performed really poorly. And also, root mean squared logarithmic error was much more higher than what we expected, so we moved on to support vector regression analysis. Support vector regression analysis is basically an extension for support vector machines, a classification method, and in this problem, just to cover the nonlinear relationship between our independent functions, we use radial basis kernels, and we use time-fold cross-validation just to prevent overfitting in our problem, and we tuned our parameters of the RBF by using genetic algorithm in the end, and root mean squared logarithmic error became much more less compared to the Mars, and this is the resulting heat map of our support vector regression. Now, dark points here are the highest backsolve predicted values from our past data, and as you can see, it was able to capture the essence of the data because of basically these yellow points. Especially these points are here, as you see, even though they have high yield points, because of the fact that they have really high relative maturity values, the support regression predicts really low backsolve values for them. And as our results from this, as you can see here, the 10 varieties performing best, and out of these 10 varieties, we chose 4 of them to be as graduates, as we were expected to graduate maximum 15% of them. So as our concluding remarks, what we did was we obtained from the grading algorithm some adjusted yield values to be used in the regression analysis, and we use radial basis kernels just to get the idea of how much they will be sold if they will be commercialized. And also one important point that new J values can be used, the inflatedness values that we cannot use, can be used by the Syngenta just to understand the locations, conditions, and compare what is actually different in some different locations. And we're still working on some aspects of the project where in this current solution, we aggregate all of the replications into one single value, and maybe we thought that it would be better just to find different values from different yield, different years. So we're working on them still. It's still in the process, and also we're doing some missing value imputation just to have some better results in this problem. Now, this will be all for my presentation. Now we'll be happy to answer your questions.